Welcome to Trigonometric Identities. Now, what is an identity? Let's go through that first, which is right here. This is right out of your textbook. This is a trigonometric equation that is true for all permissible values of the variable. What does that mean? That means if you put in an x, a value for x, left side equals right side. Huh? What are you talking about? Look, I'll write it in nice simple English here. It says an equation that's satisfied for all values of a variable, meaning the left-hand side will equal the right-hand side. You've done something like this before. I will show you. For example, if I look at just plain old simple numbers like 2 plus 3, you know and I know that it equals to 5, but doesn't 6 minus 1 also equal to 5? That's what an identity is. The only unfortunate thing is you're not going to be dealing with such simplistic numbers. You're going to deal with things like sine and cosine, maybe tangent squared, secant squared, and so on and so on and so on and so forth, because these are trigonometric identities. But the same idea holds. Left-hand side has to equal the right-hand side. But here's the thing. It's not always obvious. It's not always obvious that both sides equal each other. So you got to play around with these nice little equations, work them out, and see if you can make left side equal to right side. Well, how do we do that? 3 different ways. Number one, you can do this graphically. Take your left-hand side, put it under y1. Take your right-hand side, put it under y2. Throw them onto your calculator. If you get only one graph, guess what? It's an identity and it works. But if you have 2 graphs, not an identity. Very, very simple, okay? So what's a really cool identity to try? Let me show you. A great example would be this right here. Look, this is actually an identity, and I'll prove it to you using the calculator. So take this guy here, make him y1. Take this guy here, make him y2. And guess what? If you compare the graphs, it should work, just like I did here. y1, y2. There it is. Now, I just happen to have it already in my calculator. Now, what you should see is you're going to see this wonderful little blue graph right here, and then over top of it is this red graph. Watch, and you'll be astonished and amazed. Okay, let me just erase that. Boom. Let's go. Graph. Watch. There's the blue, and right over top of it, there's the red, telling you that this is, in fact, exactly the same thing. So, you're going, that's neat. How do you prove that that's the same thing? Well, there's another way of proving it. Another way of kind of proving it, but it will only be limited. It'll be limited to the choice that you make. Well, what do I mean by that? For example, look, if I let x equal to pi over 3, or let x equal to 2.3, I want to verify that my left-hand side equals my right-hand side. Let's try it. Let's try it first with pi over 3. So what do I got here? I got sine of pi over 3. And wait a second, sine over pi over 3. I know I can figure that out right away. I know on my little block here, pi over 3 is right there. There's my pi over 3, and it has coordinates, of course, of 1/2 root 3 over 2. So I can actually say that this is root 3 over 2. How pretty, beautiful. Let's prove that this actually is root 3 over 2 as well. So we're going to do a little bit of work on this first, okay? So let's do the work first. First things first, I got pi minus, let's substitute in the pi over 3. Okay, there's pi over 3. Common denominator time, oh yeah. Multiply that by 3, multiply that by 3. This is 3 pi over 3 minus pi over 3 to give me 2 pi over 3. Now, I know what you're thinking. How is this the same as what I've got down here? How is it the same? Well, wait, this was sine pi over 3. How is this the same value as sine 2 pi over 3? Well, simple. Draw your nice little unit circle, and you'll see there's the pi over 3's right there, remember? Okay, there's the pi over 3, which has coordinates of 1/2 root 3 over 2, and you know already that sine is that, but take a look at over here. When you have 2 pi over 3, what are the coordinates of that guy? Yeah, it's minus 1/2 root 3 over 2. So in fact, they do have exactly the same value. This is root 3 over 2. That's root 3 over 2. You proved it, but remember, this is just proving it for one case. That's the limited part of numerical values. That's very, very limited. It works for just this one case. I'll do it again over here. Watch. I'll try it for 2.3. So we want the sine of 2.3 equals to the sine of pi minus 2.3. Now, remember, this is only to one significant digit here, or one decimal place, two significant digits, right? So honestly, you should only round to, yeah, I guess, to one decimal place, and it should work out. Well, this is because this is going to give you an approximate answer. Let's try anyways. Sine of 2.3. Here we go. Let's go in here. Sine of 2.3. Sine of 2.3 bracket. Let's go. Boom. Gives me 0.7457. And the other one, if you remember, was the sine of pi minus 2.3. Let's see what happens. Sine of pi minus 2.3 should give us approximately the same value. And in fact, it does. Look at that. Oh, it gives us exactly the same value. Oh, look how pretty that is, of course. But rounding it, you'll see, look at the values are all the same all the way down. How incredibly beautiful is that? So again, that only proves this, though, for one value, and that's the value 2.3, or another value of pi over 3. Doesn't prove it for all values. That's why this graphical method works just beautifully. It proves it for all values because of the fact that the two graphs are one on top of the other. The third way of doing this is algebraically. This is where you're going to actually use a whole group of known identities and algebra, and you're going to go left-hand side equals right-hand side. And the way you're going to do it is you're going to manipulate them until you get them equal to each other, okay? When you get them equal to each other, this is the key part right there. Right there. It's valid for all variables of the unknown. Now, I could show you this one right now. I could show you this example right here that we did algebraically, but this is like going from crawling to running a marathon. You just can't jump right away. So the next couple of podcasts are going to take things nice and slow. I'm going to introduce you to this, and then I'll go back and I'll actually prove that this is, in fact, an identity, and you'll be surprised. Hang tough.